flows. When water flows in a particular direction, a water current is created. Water flows from higher levels to lower levels. A pump can push the water from a lower level back up to a higher level. The water pump is a kind of energy converter. It increases the potential energy of the water, so it can flow in a continuous cycle. Like water, electrical charges can also flow. When the charge in a copper wire flows in one direction, an electric current is created. Like water currents, electric currents flow continually through the different components along their path. The arrangement of components through which an electric current flows is known as a circuit. Light bulbs convert electrical energy into light energy and heat energy. To light up a bulb, we need a dry cell to provide energy. Dry cells contain chemical energy. When a chemical reaction occurs inside the dry cell, the chemical energy is converted into electrical energy that drives an electric current. To light up the bulb, we need to pass an electric current through it. The electric current has to flow continually in a circuit. So, apart from a dry cell and a light bulb, we need pieces of wire linking them up to form a circuit. An arrangement of a circuit that allows an electric current to flow through all the components in a complete cycle is known as a closed circuit. To light up a light bulb, we have to use a closed circuit and a dry cell. The lighting up of the bulb shows that an electric current is flowing through it and through the circuit. If the wire connecting the light bulb and the dry cell is removed, the electric current cannot flow in a complete cycle. The circuit is broken and the electric current stops. This is known as an open circuit. Electric currents can only flow through some materials. The materials through which an electric current can flow are known as conductors. If other materials are connected within a circuit, the light bulb in the circuit does not light up, even though a dry cell has been inserted and a closed circuit has been created. Materials through which electric currents cannot flow are known as insulators. Matter is made up of particles. When we break matter into its smallest components, we end up with a particle that, under normal circumstances, can be broken down no further. This particle is known as an atom. In an atom, a positively charged nucleus is surrounded by negatively charged electrons moving in orbit. In a conductor, some electrons can move between these atoms. These freely moving electrons are known as free electrons. Their freedom to move around results in conductivity, which enables an electric current to flow through the material. In an insulator, the situation is different. Here, the electrons cannot move freely between the atoms. As a result, electric currents cannot pass through insulators. We can insert a device into a circuit to make or break the circuit at will. This device is known as a switch. This type of switch, often used in laboratories, is made up of a piece of slit copper and a copper plug. When the plug is taken out, the circuit is open. When the copper plug is inserted into the slit, the plug connects the two sides of the slit. A closed circuit is formed. And the light bulb in the circuit lights up. The knife switch is another common switch in laboratories. It operates on a similar principle. When an electric current flows through a closed circuit, the light bulb is lit up. The larger the current, the brighter the light bulb and the greater amount of electric charge flowing through it. To measure the electric current in the circuit, we can add an ammeter to the circuit. An ammeter is an instrument for measuring electric current. When connecting an ammeter to the circuit, place the positive knob against the positive terminal of the dry cell and the negative knob against the negative terminal of the dry cell. The pointer of the ammeter moves and the reading shows the value of the electric current in the circuit. A unit of measurement for the electric current is known as an ampere. It's represented by the symbol A. 1 ampere is a relatively large amount of electric current. For example, the electric current flowing through a domestic washing machine is approximately 5 amperes. A smaller unit of measurement for electric current is the milliampere. 1 milliampere equals 1,000th of an ampere. The electric current flowing through a light bulb ranges from approximately 200 milliamperes to 500 milliamperes. Dry cells store chemical energy. In a closed circuit, the chemical energy in the dry cell is converted into electrical energy to drive the electric current through the circuit. Dry cells can drive electric currents because they generate a voltage. When a circuit is connected by 2 dry cells, the light bulb in the circuit becomes brighter. The greater brightness is a result of the higher voltage. Within a circuit, the higher the dry cell's voltage, the larger the electric current. If the number of dry cells in the circuit is increased to 3, the voltage further increases, the electric current becomes even larger, and the light bulb much brighter. Voltage in a circuit is measured by a voltmeter. The unit of measurement for voltage is the volt, and the symbol for it is V. To measure voltage, connect the positive and negative knob of the voltmeter to the positive terminal and the negative terminal of the dry cell respectively. The voltmeter's pointer shows the voltage of the dry cell. At the same time, the ammeter in the circuit shows the electric current. The conductivity of materials varies. This means that electric charges pass through some materials more readily than through others. The tendency of a substance to resist the flow of an electric current is known as resistance. The unit of measurement for resistance is ohm, and the symbol for it is omega. The resistance of materials varies. Copper is a highly conductive element with low resistance. Nichrome is about 80 times more resistant than a piece of copper of the same shape and length. In some situations, the same substance may vary in resistance. This circuit is composed of a dry cell, an ammeter, a light bulb, and a nichrome wire. An electric current flows from one end into the nichrome wire, out through the sliding contact on the other end, and then through other components to form a closed circuit. Change the position of the sliding contact, and the length of the nichrome wire in the circuit is changed. When the sliding contact is moved to increase the length of the nichrome wire, the ammeter reading reveals that the electric current is smaller. On the other hand, when the length of the nichrome wire in the circuit is reduced, the ammeter reading goes up, showing that the electric current is larger. From this experiment, we can deduce that when an electric current flows through a substance, its resistance increases and the electric current passing through it decreases as the length of the substance changes. There's a metal wire in this closed circuit. If the wire is replaced by a thicker one made of the same metal, the ammeter shows a larger reading and the light bulb is brighter. This is similar to the situation in which a thick water pipe, where water flow is greater than in a thin pipe, or a wider road carrying a greater traffic flow than a narrow road. From this experiment, it can be deduced that resistance and electric current decreases and increases as the diameter of the substance changes. A rheostat is a component that allows us to vary the resistance. Place a rheostat in a circuit. When the rheostat is adjusted, the reading of the ammeter and the brightness of the light bulb vary. By changing the resistance, a rheostat increases or decreases the electric current in a circuit. The resistance can be changed by moving the sliding contact. The insulated coil in the rheostat is a resistant coil. When the sliding contact is moved to the right, the electric current first goes through the copper rod and then through the resistant coil. As the electric current is flowing through just a small portion of the resistant coil in the rheostat, the resistance in the circuit is relatively low, resulting in a large electric current. If we move the sliding contact to the left, the electric current flows through more of the resistant coil. The resistance in the circuit is increased and the electric current becomes smaller. If we move the sliding contact to the far left, the electric current flows through the rheostat's entire resistant coil. Here the resistance in the circuit is at its maximum and the electric current is smallest. The dimmers in household appliances, theater stage equipment, and control consoles make use of such varying resistance to adjust brightness and volume. We use symbols to represent objects. These circuit symbols are used to represent different components of a circuit. We use different circuit symbols to represent the dry cell, battery, light bulb, rheostat, switch, voltmeter, and ammeter. If we use a straight line to represent a conducting wire linking up the components, the whole circuit is represented as a circuit diagram. We can also use various components to construct a circuit from a circuit diagram. Two identical light bulbs are connected to a circuit. The electric current has to follow a single path to get through the various components. The current passing through the two light bulbs is the same. The two light bulbs are equally bright. This way of connecting two light bulbs one after another in the circuit is known as connecting in series or a series circuit. In a series circuit, the electric current is the same at every point of the circuit. If we remove one of the bulbs, the circuit is broken and the other light bulb goes out immediately. The two light bulbs can also be connected in parallel in the circuit. If the two bulbs are of the same type, the electric current flowing through the light bulbs will be of equal strength. The bulbs will also be equally bright. But the electric current drawn from the dry cell is double that passing through each light bulb. This way of connecting two light bulbs is known as connecting in parallel or a parallel circuit. In a parallel circuit, there are two or more branches of electric current. The total current in the circuit equals the sum of the current in all the branches. When one of the light bulbs in a parallel circuit is removed, the electric current still passes through the other branch. The brightness of the light bulb remains unchanged. If we put in two light bulbs of different resistances, The two branches of the circuit have different resistances. The current flowing through the light bulb with a greater resistance is smaller and the bulb is dimmer. The light bulb with a smaller resistance allows a larger current to flow through, so it is brighter. This experiment shows that in a parallel circuit, the electric current is larger in a branch with smaller resistance and smaller in a branch with greater resistance. When an electric current flows through the resistant coil in a circuit, energy conversion takes place. In an open circuit, there is no obvious change in the resistant coil. If the circuit is closed, electric current flows through the resistant coil. The resistant coil is heated up and heat energy is released. As a result of the heating effect of the electric current, the resistant coil converts electrical energy into heat energy. If the electric current is larger, the resistant coil becomes hotter. If the current is larger still, it becomes hotter still. Many electrical appliances, including rice cookers, electric heaters, and hot plates, use the heating effect of electric currents to generate heat energy. There is a single light bulb in this circuit. An electric current flows through the light bulb and lights it up. Adjust the rheostat in the circuit to gradually increase the electric current flowing through the light bulb. The brightness of the light bulb increases gradually until the filament burns out. In a series circuit, connect a thin resistant coil immediately in front of the light bulb. When the electric current in the circuit increases, the resistant coil and the filament light up at the same time. Before the current increases to a level large enough to burn out the filament, the intense heat will burn out the resistant coil. The current is cut off immediately. This prevents too large a current from burning out the filament in the light bulb. In every circuit component or electrical appliance, there is a preset current rating. As long as a current does not exceed the current rating passes through the component or appliance, it works. Too large a current can damage the component or appliance. If we connect a thin resistant coil in series to the circuit before the electrical appliance, the size of the current is restricted by the current rating of the resistant coil. In the case of a short circuit, when the current exceeds the current rating of the resistant coil burns out. In this manner, the resistant coil protects the electrical appliance from overloading. Hence, a thin resistant coil can serve as a fuse wire. In everyday applications, it's more convenient to use a circuit breaker to provide a similar protection to a circuit. Circuit breakers can be either electromagnetic devices or bimetallic strips. When the current in a circuit becomes too strong, the circuit breaker breaks the circuit. Once the problem is rectified, the circuit can be reconnected by pushing the switch on the circuit breaker.